All right, so thank you very much for inviting me to Bilbao, to this conference. I've enjoyed what I've seen today. Unfortunately, I missed the first 2 days because of snow in Bristol. When you get 3 inches of snow in the UK, all of the airports close. Okay, so my talk is about simulating the vibrational quantum dynamics of molecules with photonics. This is work that was experimental work that was done in Bristol and carried out with all of these collaborators. It's also work that is still under review, so I'd be grateful if you don't sort of tweet about it or put it on the internet or anything. Yeah. All right, so the way that atoms vibrate in molecules underpins a lot of their key behavior, such as dissociation, for example. When lasers were invented, experimental chemists became very excited because they thought that, well, this is a great new way to disassociate molecules. You could just look for the bond energy that you want to break up, take a monochromatic laser, tune it to that energy, and then the molecule will fly apart, right? But it didn't work. And the reason it didn't work is because the rapid molecular vibrations redistribute that energy really quickly. So all that happens is the molecule thermalizes, and just the weak bonds, the uninteresting bonds, get broken. So then a breakthrough, a sort of theoretical breakthrough was made when it was realized that, well, the reason that this is happening is because it's the quantum evolution of the vibrations in the molecule. So probably what you want to do is shape a laser pulse, hit that on the molecule, and excite an interference pattern such that after some period of evolution, the excitations will all end up in some local bond, and the dissociation will happen. The bit of the molecule that you want to fly off will happen, which is a great idea. It seemed like it was solved, but actually that also didn't work. And the reason, obviously, is that real molecules are more complicated than the models that we have for them, and there are environmental effects as well. So, Rabitz and other people came up with this, I guess, machine learning scheme, effectively, which is to say, well, okay, what we should do is just either start off with a laser pulse that's a guess, that we guess will perform the dissociation, or just even start with a random laser pulse, shine it onto a gas of molecules, and then look for some signal, and look for some sort of dissociative signal, signal of the molecules breaking apart. And then, try to tweak the laser pulse a bit. And if you get more signal, then keep going in this direction. Or if not, then you need to try another direction. So this sort of closed-loop machine learning protocol. And this worked sort of reasonably well. And in the late 90s, this kind of experiment was performed where chemists took this molecule. I don't know what that molecule is, but that's the description of it. And we're able to, either by selecting one type of laser pulse or another type of laser pulse, tune the relative proportion of whether they dissociate into the, basically tune the ratio, high or low ratio of these two product states. Okay, and then, fast forwarding a bit further, it seems that, even a single quantum of vibration can strongly influence the kind of dissociation that you get in molecules. So a favorite molecule for quantum chemists is NH3, or ammonia. And what they like to do is dissociate this into NH2 and a hydrogen atom. And so, a way of understanding this process is through these two potential energy curves here. So the potential energy surface at the bottom is the ammonia molecule in its electronic ground state. And the potential energy surface at the top is the NH3 molecule in its electronic excited state. These axes here, this one along here is basically the distance of one of the hydrogens away from the nitrogen. So it's a local stretch mode, the distance of a local stretch going on. And this theta here is the angle of an umbrella vibration. So it's sort of all of the hydrogens are going up and down together. And so across these two axes, you can plot these potential energy curves. Okay, so the way the experiment goes is that you take an NH3 molecule and excite it electronically up to this top potential energy surface. And then it can dissociate in either one of two ways. Staying on the top potential energy surface, which is known as the adiabatic pathway, what happens is the NH2 that you get remains in the electron excited state, and you get a slow hydrogen atom sort of popping off. Alternatively, we can pass through this conical intersection, and the NH2 drops into an electronic ground state, but you get a fast hydrogen atom. This is the non-adiabatic pathway. Okay, so the cool thing is that it turns out that you can tune between these two pathways with a prior stretch excitation. So before exciting to the electronic excited state with a UV pulse, if you have with an infrared pulse initiated an anti-symmetric stretch into the modes, then what you find is that you follow more often than not, the molecule follows the adiabatic pathway. If, however, a symmetric stretch, that's the anti-symmetric stretch. If a symmetric stretch has been excited, or some of the other vibrations as well, then you're much more likely to go through this conical intersection and end up with ground state NH2 and a fast hydrogen atom. And so in recent years, there's been really impressive advances in quantum chemistry and chemistry with control over these vibrational wave packets, so this pulse shaping. Now we have manipulation of individual molecules at ambient temperatures. Preparation of coherent superpositions on sub-femtosecond time scales. And with this sort of scanning tunneling microscopy, techniques to observe these molecular dynamics on their intrinsic ultrafast timescales. There's also the tantalizing prospect of molecular control with quantum states of light. So not just sort of shaping classical pulses, but sort of constructing really delicate and interesting quantum states of light that could really perform some interesting quantum operation on a molecule. So in here, this is with microwave light, not infrared light, but they managed to use squeezed microwave light to cool down a microresonator to below the back action limit. It's been theoretically shown that entangled states of two photons can lead to an enhanced two-photon absorption in spectroscopy, and sort of in an analogous fashion to shaping the pulses of lasers. New techniques are being put forward to shape the characteristics of single photons. Okay, so what about the sort of the computational complexity of simulating molecular dynamics? Well, think about it in the simplest picture, which is the harmonic approximation. So I showed you those very complicated potential energy surfaces earlier. One basic model is to take those potential energy surfaces and sort of fit the bottom of them to a quadratic potential. You end up with the Hamiltonian of 3n, where n is the number of atoms, minus 6 uncoupled harmonic oscillators. So you've got this sort of nicely diagonalized Hamiltonian. So then you might naively think, well, okay, the Hamiltonian's solved, so surely the dynamics are tractable classically, but it's not necessarily the case. In fact, it's not the case. So consider a transition of local excitations, for example. So this picture here is a sort of a decomposition of molecular vibrations. In the center, we've got the normal mode vibrations. So those are the ones that if you put it into that state, it will remain in that vibrational state. We also have local vibrations. So for example, with a carbon dioxide atom, you might have one of the oxygens in a local stretch as a superposition of a symmetric stretch and an asymmetric stretch. So these local mode superpositions, these local vibrations are superpositions of the normal mode vibrations. Okay, now let's consider exciting, taking this molecule, this is H2CS, which is thioformaldehyde. Let's consider taking this and exciting the two hydrogens, each with a quantum of energy, so with a quantum of vibration. And then asking the question, okay, what is the probability to having excited that double vibration after some period of evolution, the state remaining in that vibrational state, two local vibrations? Well, the unitary is given by just the exponentiated Hamiltonian for some time, for the time that the thing's evolved, pre and post multiplied by these local mode transformations. So that's a transfer unitary on vibrational modes. Phonons, these vibrations, phonons are bosons, and they're non-interacting bosons when we're in this harmonic approximation. And so the probability, or the probability amplitude to observe this transition is just given by the permanent of the 2x2 submatrix within that overall unitary. So of course, the complexity is really just like boson sampling at least for large molecules with many excitations, and if the period of evolution was such that the whole unitary looked like a random unitary matrix, then it would be very close to boson sampling in terms of complexity. And as Fabio mentioned earlier on, there's been a whole bunch of experiments started with these four in boson sampling. And it's sort of already tells a story really that a nice platform for simulating molecular dynamics, vibrational dynamics is linear optics. There's this nice recipe from Reck et al. From 1994 for decomposing an arbitrary, basically what it says is with this array of Mach-Zehnder interferometers, you can implement any linear optical transformation imaginable just by tuning the phase shifters. So it works in a sort of really nicely intuitive way. You can imagine injecting laser light into this top mode, and then with the first, this is a beam splitter, but it's sort of represents this Mach-Zehnder interferometer, which is a beam splitter with tunable reflectivity. So by tuning the reflectivity of this guy, having input laser light here, we can just keep the amount of laser power that we want in this upper mode and dump the rest into the second mode. Then with the second beam splitter, we do the same again, just keep the same amount of power that we want in the second mode, and so on. And we can also put phase shifts as well on these modes. So we can put laser light in here and dial up any vector that we want just with this diagonal bank of Mach-Zehnder interferometers. Then we can come along to the second input mode and do exactly the same thing on another laser beam. Obviously, we do this on single photons, not on laser beams, but that sort of gives a nice idea, an intuitive idea of how this decomposition works. Again, as Fabio showed, we implemented this in this chip. So this is a silica, or silicon dioxide, or glass chip on a silicon substrate. It was fabricated by NTT in Japan, and it allows an arbitrary unitary operation over 6 optical modes controlled via 30 thermo-optic phase shifters that control 15 Mach-Zehnder interferometers. We just use the kind of spontaneous parametric down conversion source shown in Fabio's source and detect photons with silicon avalanche photodiodes. So that the secret with this chip is that it doesn't really look like this. To fit this thing onto a 6-inch wafer, the guys at NTT actually had to bend the thing in half. And I was actually sort of frightened when I heard that they were going to do this, but it seems to work. They obviously know what they're doing. Okay, so these are some technicalities for those people that are interested. All right, so then how do we map the molecule to the chip? Well, the first stage is to calculate the Hessian of the molecule, which is just the second-order derivatives of the electronic energy with respect to nuclear coordinates at equilibrium geometry. Then diagonalize that thing in mass-equated coordinates, and from that you can get the normal mode frequencies. So we can just easily get this diagonalized Hamiltonian. Okay, then what we want to do is to get the transfer matrices to local modes, and this is found by numerically maximizing sum of squares of kinetic energy from each nucleus. Then having got this, we can just times these things together and get this time-dependent unitary. We just map that unitary to the phase shifters in our chip. Okay, so the simulation sort of works really easily. We just take the waveguide that corresponds to the particular vibrational mode that we want to initiate the simulation in. And then if we're putting one quanta of vibration, if we're simulating one quanta of vibration in this mode, then we just stick one photon into that waveguide, and then just dial up this unitary for a sequence of time steps and plot this curve. So we just track the unitary dynamics of a single excitation, in this case in thioformaldehyde, a single local excitation evolving for 30 femtoseconds. And in fact, we don't need to sort of restrict ourselves to like true analog simulations where, if you want to simulate 300 femtoseconds, you have to actually run the whole thing for 300 femtoseconds. We can skip along, so we can simulate 30 femtoseconds, skip along 100 femtoseconds, and then do another 30, and sort of coarse grain or fine grain the statistics as we like, and observe these statistics over two different time scales. All right, so then it gets a bit more interesting when we think about simulating multiple excitations. So this state here, this superposition of two photons, a pair of photons in two modes, plus 4 photons in two modes. This is really what we just get directly out of the spontaneous parametric downconversion source. And what it simulates is, in these local modes, two single excitations, or a single excitation in each of two modes, or a double excitation in each of these two modes. So if we start the simulation and then again plot these curves, what we're looking at here is the probability to having input two single photons to remain in the input state, which is just these two localized stretch modes, or for the energy to transfer to two bend modes, or for the energy to transfer to a bend and a stretch mode. That's what the gray line is. And it's a similar situation for the two doubly excited modes. And the versatility of this kind of simulation is such that we can dial up any 4-atom molecule. So a 4-atom molecule in general has 6 vibrational modes. And so we chose a selection here of different molecules that have different sort of intrinsic time scales. I can't remember the actual names of these molecules. But I guess because of the structure of these ones, maybe it's more rigid. We end up with these slow vibrational oscillations, whereas down here we've got these really sort of fast vibrational oscillations. Okay, so sort of going beyond idealized models, in reality, molecules thermalize. They interact through intra and intermolecular interactions and lose energy. So this is a water molecule, H2O. It has 3 vibrational modes, a symmetric stretch and an anti-symmetric stretch, and then a bend mode. Energy is lost either directly from the stretch mode to the ground state or via the bending mode to the ground state. And the way we model this is not through a Hamiltonian, but through a Lindblad type master equation to simulate or to model amplitude damping, which leads not to unitary dynamics, but Krauss operators and non-unitary dynamics. So then you think, well, what I have in the lab is unitary. How do I implement a non-unitary when what I've got is unitary? Well, there's this trick called unitary dilation, which says that you can embed any n by n matrix inside a unitary that's 2n by 2n. So if we have a 6 by 6 unitary operation in the lab, which is what we do, then we can implement any 3 by 3 matrix. It doesn't need to be unitary. And so we can implement these Krauss operators that give this kind of evolution and simulate this thermalization. So we initiate in a superposition. So a local stretch mode, which is a superposition of a stretch and an anti-stretch. And then we sort of watch the energy just dissipate. Some of it goes to the other local stretch mode. Some of it goes to the bend mode. But in the end, it sort of all leaks out, and we end up in this ground state. Also going beyond ideal models, I showed earlier these more complicated realistic potentials that we get that aren't really harmonics. An example of a less easy potential is an anharmonic potential. And so this is described not only with quadratic terms, but also with including third order and semi-diagonal quartics into the Hamiltonian, so it's just interactions. And now what this means is that, before we could get away with our photons not interacting. Here, if you want to simulate anharmonic potentials, then we need interactions between our photons, and obviously photons don't like to interact. There's this trick in linear optics that allows you to implement measurement-induced nonlinearities with ancilla photons. So you take the two photons that you want to interact, and you put in an ancilla photon, and then with some probability, when you detect the ancilla photon in the correct place, then the measurement, then the interaction is being implemented on the two sort of computational photons or simulation photons in this case. I guess one way to think about anharmonics here is that, well, in the harmonic case, if you were to put, the energy levels are equally spaced in the harmonic case, right? So that you've got to think how does that translate to phase shifts? Well, I just put one photon in and I get an alpha phase shift. Then what I want is when I put two photons in to get a 2 alpha phase shift. That's the harmonic approximation. In the anharmonic approximation, when you put one photon, you want the alpha phase shift. But when you put two in, you want something less than a 2 alpha phase shift. The energy levels get tighter as the potential goes up in the anharmonic case. Okay, so we were able to find a scheme that implements these sort of weak phase shifts with measurement-induced nonlinearities and simulate evolution under an anharmonic potential. So we initiated the simulation with two excitations in the local stretch mode and the ancilla photon, of course, and then observed the oscillation of, this is the oscillation of a photon in each, so sort of the anti-bunch case, a photon in each local stretch mode. So you can see the probability starts at 0 because we don't initialize in that state, but then it grows and it oscillates. The dotted line is the harmonic case, and the solid line, the dotted line is the harmonic case, the solid line is the anharmonic case. So in this case, they sort of closely match, they're just sort of slightly out of phase. But here, looking at the probability to find again the two photons in the local stretch mode that we initiated in, you can see that the two statistics between harmonic and anharmonic start to get quite different. So, including these anharmonicities becomes important. Okay, then finally, onto the machine learning part. Well, thinking back to that example I showed earlier on from the quantum chemistry experiments, what we wanted to do was to try to design a quantum control field that would lead to an interesting kind of disassociation. So we want to find a preferred path to a kind of disassociation. Okay, so this is our simplified model. We have these two potentials. In the real experiment, we'd have the anharmonic potential. Here, we just used the harmonic one. So we've got a harmonic electronic ground state potential and a harmonic excited state potential. And if you recall, in the chemistry experiments, they excite between these two potentials with a UV pulse. So what we want to do is find what kind of vibrational state do we want to excite such that after simulating the lift to the electronic excited state and over some period of evolution, we get to some preferred disassociation. So in this case, what we're looking for is we're looking for two photons to bunch. What state do we initialize in such that over a period of 10 femtoseconds, we find an on average higher probability of getting two photons into a local NH stretch mode and bunching nowhere else. So we want to, as much as we can, we want to prefer this kind of disassociation and not invite other kinds of disassociation. So this is the kind of protocol, I guess it's fairly familiar. We initialize with a random state, which is what we do here. Then implement a unitary that transfers between the two potentials to the electronic excited state. Simulate some period of evolution, and then measure again in the local basis. And then measure the statistics, evaluate some cost function, and update the initial vibrational state based on some Nelda-Mead algorithm. And so these are the results. So let me get this right. So this is basically the thing getting better with over 400 iterations. But this is where we start off. This is the state that we try to sort of our initial state, our initial guess, which is just a random two photon state in this case. And what we find is that in the random case, over 10 femtoseconds, these blue bars the non-NH bunching. So these are the events that we don't want. And in the initial trial, we get sort of lots of these events that we don't want. But then, we use Nelda-Mead, and about 200 iterations later, we're at this trial state now. And we're starting to see some red, which is the NH bunching that we do want, and a minimization of the non-NH bunching. And then by the end, after 400 iterations, what we're finding is that we can find a state such that over the full 10 femtoseconds, the NH bunching is quite reasonable. We don't see hardly any non-NH bunching, and we see some of this anti-bunch, which is sort of benign. Okay, so that's sort of pretty much it in terms of the simulations, and I wanted to find a sort of a neat way to segue to this next slide, but I couldn't really think of one. It basically just addresses, how difficult is it going to be to scale up these kinds of simulations. So this is like the results of some work that we did last year, which looks at, pitting classical boson sampling algorithms against experiments. And so the gist of it is that on this axis, we're looking at photon numbers generated at a 10 gigahertz rate. And then on this axis, we're looking at, okay, what kind of transmission probability or what kind of 1 minus loss can we afford? And what you find, and this curve here is a quantum advantage curve. So this is like just when the experiment is outperforming the classical algorithm. But with the quantum advantage, it could be the case that, with a few tweaks to the classical algorithm or the hardware, you could, maybe the classical machine would sort of get back in front. We've got these two regions of quantum supremacy, which are basically saying that the advantage is so great that we wouldn't believe that any tweaks to the classical algorithms or hardware could ever hope to match the quantum machine. And so what we found is that if you can get the losses down to about 50%, then you start to see quantum advantage at around 20 photons. But if you want to see quantum supremacy, then what you want to do is to get up into the region of 50, 60 photons. We define these two regions of quantum supremacy. Quantum supremacy 1, which is basically saying that the quantum advantage is like 2 orders of magnitude greater. And quantum computational supremacy 2, which is basically saying, well, what we want is a problem that the experiment could solve in a week, but the classical algorithm would take 100 years to solve, so like a practical quantum supremacy. And I guess the gist is that it could be the case that what we need is some error correction. Maybe this is what this is telling us, some basic error correction methods for photon loss. But the hope is that what we don't need is the full-blown error correction like you need for full-blown digital quantum computing. Hopefully we could get away with something much less demanding and still get into this quantum advantage regime. And just as a last slide, I wanted to show sort of a recently published chip as an idea of sort of where we are with complexity of integrated photonics, and maybe the kind of complexity that will allow us to implement some of these error correction protocols. So this chip, this is actually, it's only a 2-photon chip. It generates 2 highly entangled photons, but it does it across these 16 sources. So we end up with 2 16 D qubits that are entangled, and it has some sort of measurement circuitry here at the end. All right, so that's the end of my talk, and thank you very much for listening.
Thank you. All right, questions? Yeah, Andrew?
On those curves, the very nice curves you showed, you had the theory curves and experimental points. And not all the experimental points were sitting on the theory curves. Do you have a sense of why they're varying off and how that will vary with scale?
Can I go back? Can you remember?
That kind of thing, yeah.
Here?
No, yeah. So, not all of the blue points are on the blue curves, for example. Do you have a sense of why they're varying and how that will change as you scale to more and more bosons?
So I guess we could try harder just to sort of calibrate the chip. I guess it's just not giving perfect unitaries, So we have like it's just a simple explanation, really. We have like the target unitary that we'd like to get to, and we're a bit off, but it's not too bad. Fidelities are probably like 96, 97%. So for sure, a bigger version of that chip isn't really going, with many photons, probably the fidelities will start to drop off a bit, I would imagine.
Nathan?
In defense of your blue curves over there,
yep.
Just eyeballing it, it looks like the line's going through roughly 2/3 of the data points.
Sorry, I missed that.
Roughly, it looks like the lines are going through 2/3 of the data points. And
Yeah.
if those lines correspond to a single sigma, if you were doing better than that, that would actually be quite scary. So,
Yes.
so I think that's actually, it looks okay at first glance, but there could be some oddities, like
Yeah.
Andrew's suggesting.
Yeah.
One question I just was hoping you could clarify also to me about the propagation with this. Because you can't go kind of deep in time with your analog simulation here, are you pre-programming what unitary you would expect for that time and then just dialing that into the system? Is that how I should be interpreting the evolution on the bottom?
Yeah, so we're just dialing up the unitary so we could go forward to any time that you want. We don't need to start at time 0. You could say, just give me just the one-shot statistics from 100 femtoseconds in, and we just go to that unitary and dial up that unitary.
But it relies on having a good classical simulation beforehand. Right.
Well, so you can calculate so in this case, I guess the subtlety is that you can always calculate the unitary efficiently because the unitary is sort of quite small. It's putting in the number of photons that blows up the computational space. Thank you.
All right. Any more questions? Okay, if not, then let's turn to the speaker again.